Let's get going. All right, Chemistry 3101. This is Chapter 2, Molecular Representation. So, how do we represent molecules? And if you think back to your days in General Chemistry 1, you spent a lot of time looking at Lewis structures when you studied things like molecular geometry and bonding and Vesper theory. So, Lewis structures are great, but they're really only practical for very small molecules. So, when we're dealing with large molecules, and we will look at many large molecules throughout this semester, you'll find that Lewis structures can be used, but you'll find that they're inadequate. And the reason why is because Lewis structures take a while to draw. The next is a partially condensed structure. And a partially condensed structure is one where we eliminate or we don't show the carbon-hydrogen bonds. So since we have so many carbon-hydrogen bonds in organic molecules, if we just leave those out, you can see that we eliminate a lot of work, right? We leave out, these bonds here, this bond, so on and so forth. So you can see how going from a Lewis structure to a partially condensed structure can save you, quite a bit of work, and you can, when you use a partially condensed structure. The next one is a fully condensed structure, which we just call a plain old condensed structure. It says single bonds are not drawn at all, so we leave out all single bonds, and groups of atoms, we cluster them together when we can. So if we can cluster a bunch of atoms together, we'll do it. So if you look at this molecule, you'll see that in this molecule we have two CH3 groups. Now, instead of writing both of them out in a condensed form, what we can do is, since we have this carbon here that's attached to a hydrogen, which is this one here, we can take both of those CH3 groups and we'll group them together, and then we'll put a bracket around them. So that means these two groups right here, we'll group them together, and then we put a subscript 2, and that lets the reader know that you have two CH3 groups, and then lastly we have the OH or the hydroxyl attached to that. Now, a molecular formula is great, okay? Molecular formulas are wonderful. They have their place, a molecular formula does, but the problem with a molecular formula is that it doesn't tell you anything about the structure of the compound. For example, if I have this formula right here, C3H8O, that molecular formula could actually represent 3 different molecules. It could be what's called isopropanol, which is rubbing alcohol. It could be what's called 1-propanol, and it could also be another compound, which is something completely different, called ethyl methyl ether. And so if you were to just show me a molecular formula, I'm like, well, which one of these compounds is it? So you see how you don't get any structural information from a molecular formula. With all that in mind, let's take a look at a practice problem from the book. It says, draw the Lewis structure for each of the compounds below. Well, let's just do C in the interest of time. Of course, the solutions to these are found online in the e-textbook. I showed you how to access that during the first day of class. Well, if we look at C carefully, you notice that you have 1, 2, 3 of these CH3, CH2 groups. Okay, so we have 3 of those, and each one of those is going to be bound to this carbon right here. Let's start by drawing that carbon out in green. Okay, now I'm just going to color code this. Obviously, you can draw everything out in a pencil, but or a pen, whatever. But anyhow, we're going to have 1, 2, 3 CH2, CH3 groups attached to this carbon here. So now I've just drawn the carbon. So I've just covered these 2 carbons right here. And if I fill in all of these carbons with hydrogens, right, because carbon has to have 4 bonds. If you don't know what I mean by that, if I just look at this carbon the way it's drawn, I only see 1 bond. So that means 3 plus 1 gives me 4. So that means I have to have 3 bonds to hydrogen. So 1, 2, 3. If I look at this carbon, it only has 2 bonds. So it needs 1, 2 bonds to hydrogens. Same thing for this one here. And then down here, I have my CH3 group like this. And then on the end, I have my OH, my hydroxyl. So I'll put that here like that. I'll even put in the lone pairs like that. Give me a thumbs up if you feel like you could draw a Lewis structure from a condensed structure, provided you had a little bit of time to practice. All right, great. Okay. Wunderbar. This is something that is skill that you're definitely going to have to be able to do, is to be able to take a condensed structure and draw a Lewis structure from it. So I want to go back and address a question that showed up in the chat. And a student asked, these three compounds that I said right here, they all have the same molecular formula, but they all have different structures. So with these three compounds, isopropanol, 1-propanol, and ethyl methyl ether, would they be constitutional isomers? Yes or no? Could anybody answer that? Just asking if these would be. Go ahead.
No, because they're the same thing. They're just written differently.
So the answer is yes, they are constitutional isomers. Okay. And why are they constitutional isomers? These three compounds are constitutional isomers because they all have the same molecular formula, but they are three different compounds. Okay. So these are all different compounds. And so they are, in fact, constitutional isomers. Well, let's move on from there and let's get into what's called a bond line structure. Now, sometimes you'll hear bond line structures. If you're the kind of person that likes to Google everything or look up everything on YouTube or get a second opinion about everything, sometimes you'll hear these called skeletal. So skeletal structures, they call them sometimes. I cut my teeth on bond line structures, so that's what I'll call them. If we look at this structure down here, it says Lewis structures are too impractical to represent a compound like amoxicillin because of its size. You see that amoxicillin is actually quite a large compound. It's definitely not the largest compound we'll look at, but it's big enough. But if you were to draw a condensed formula of this, that would tell you very little about the actual molecular geometry or the shape of the molecule. Now, amoxicillin is an antibacterial that's used to treat many different bacterial infections, and it's one of the most commonly prescribed antibiotics in children. Very cheap, only costs, I don't know, a couple of cents for one pill, something like that. Anyhow, and amoxicillin is also part of a class of compounds called beta-lactams. That's neither here nor there. But the idea is that if you had to draw this structure for amoxicillin, let's say you were working as an organic chemist and you were working on amoxicillin derivatives, let's say, well, drawing this out every time would take a lot of work. So, it's just like those infomercials, right? There's got to be a better way. And the answer is yes, there is. So for 1995, you can learn how to draw the bond line structure. And you see the bond line structure down here at the bottom. And again, we also call it a skeletal structure. It's much easier to read and to draw. Now, what do I mean by easier to read? Well, something else that we're going to take a look at today are what are called functional groups. Now, you all know that because you read the chapter before coming to class. You just couldn't wait. Okay, so we have different functional groups. And if you're like, what's a functional group? This is a functional group. This is a functional group. We have one here, so on and so forth. And our eye is drawn to those atoms that are not carbons and are not hydrogens. Okay, so you notice this sulfur a lot easier than you do in this one here, right? So not only is it easier to recognize functional groups, which are most often the points of reactivity in a molecule, but it's also easier to draw. You can draw this I could draw that about 10 times faster, maybe more, maybe 25 times faster than I can the entire Lewis structure. So now we're going to look at, what do all these lines mean exactly? How do we read a bond line structure and how do we draw a bond line structure? Well, bond line structures are in fact the benchmark representations for organic compounds. It says it is critical to known, it's actually critical not to known, it's critical to know how to draw these structures for any compound without difficulty to succeed in any organic chemistry course. So critical, another word for critical that I would use would be imperative, okay? You have to know how to draw bond line structures. You can't, second guess yourself on a bond line structure in organic chemistry or you will be in a lot of trouble. Now, I'm not saying that to intimidate you because many people have taken this class before you and many people will take it after. So everybody learns how to draw bond line structures. But let me show you how we read a bond line structure. Well, we start by drawing lines, okay? And it says here that each corner, or another word for a corner would be maybe a junction, okay? So we'll call that a junction. Sometimes students will call it a vertex or something. But anyhow, each corner or endpoint represents a carbon atom. So if we look at this structure right here on the far left, you can see that it has 6 numbers on it. Well, it tells you right here that each corner represents a carbon atom. Here we have a corner, here we have a corner, here we have a corner, and here we have a corner. It also tells you that each endpoint represents a carbon. Here we have an endpoint, and here we have an endpoint. So that means I've highlighted 6 spots, so that means I have a total of 6 carbons. Now, how many bonds does carbon form? Carbon always forms 4 bonds. So if I look at carbon number 1, for example, there is a carbon here, right? We're not drawing it in because it takes too long. But it is implied that this carbon, even though you only see 1 bond, this bond here, it's implied that there are 1, 2, 3 bonds to hydrogen. So that's a CH3. If you look at this carbon right here, who could tell me how many hydrogens would be attached to carbon 2? Who's got some intuition on that? Yeah, Courtney's absolutely right. Yeah, you're absolutely right. The answer is 2. Why is it 2? Because 2 plus 2 equals 4, right? That's all I'm doing. If you look at this carbon, how many bonds are attached to that carbon? We have 1, 2 bonds. We need to have 1, 2 more bonds in order for the carbon to have a complete octet. So that's a CH2. This is a CH2, this is a CH2, this is a CH2, and this would be a CH3. Okay, so that's how we read a bond line structure. Now you notice that in that compound, there are no double bonds. You might be wondering, what do I do if there's a double bond, Mr. Dion? Well, the first thing is that when you draw a compound that has a double bond, you draw it in this zigzag pattern the same way we did with the first compound. Okay, so we have a double bond right here. Now I'm going to test you here. You can see that we have a junction here, we have a junction here, we have an endpoint here, and we have an endpoint here. So there are a total of 4 carbons in this molecule. Now we know that there's a carbon right here where the number 2 is, right? And if you want to write the letter C to represent the carbon, be my guest. My question to you is, how many carbons are directly attached to this carbon that's labeled 2? Could anybody tell me how many hydrogens are attached to that carbon? Yeah. Courtney, Kayla, Moira, Jessica, you're all correct. It's 1 hydrogen, right? There's 1 hydrogen. How do you know that, Mr. Dion? Because there's 1, 2, 3 bonds, right? A double bond counts as 2 bonds. And therefore, we have 1 hydrogen attached here. Here we have 3 hydrogens, right? That's the idea. Now, the reason why we draw a zigzag pattern when we have either all single bonds or when we have a double bond is because each one of these carbons in the molecule on the left all are sp3, and so we would draw it with a zigzag like that. Now these 2 carbons here are sp2 hybridized, and we know that they're trigonal planar, right? Their bond angle is 120 degrees, and that's why we draw that with a zigzag. But when it comes to having a triple bond, okay, when we have a triple bond, we know that the geometry in an sp hybridized carbon, I'll just draw it up here. If you have an sp hybridized carbon, we went over this in chapter 1, that this bond angle is 180 degrees. And so the carbon here and the carbon here, at number 2 and number 3, these have to have a bond angle of 180 degrees. Okay, so here's a question. How many hydrogens are attached to carbon, the one that I just circled in red, the one, carbon number 3? And it's not a trick, okay? How many? The answer is 0. Right, there are 0 hydrogens attached to that one. How do you know, Mr. Dion? Because we have 1, 2, 3, 4 bonds. If you have 4 bonds, you don't need any hydrogens, okay? We don't include hydrogens in bond line structures. All right, again, it's all repeated down here. Linear geometry is shown when we have an sp hybridized atom. Carbon atoms are not labeled, but a carbon is assumed to be located at every corner or junction or whatever you want to call it, angle, and every endpoint of the zigzag. Okay, and then hydrogen atoms are not included. Okay, now sometimes you'll see a hydrogen atom in a bond line structure, but that's specific cases, and we'll look at those. It says here that you must also be able to use the bond line structure to interpret the number and location of hydrogen atoms in a molecule. Now, this is something I already covered with you, but let's say we had this molecule shown right here. This is called 2-pentanone. You don't need to know that right now, but if you look at that carbon that's highlighted in green, that carbon, again, we know there's a carbon right here, okay? It's got 1, 2 bonds shown in the bond line structure. Remember, we leave hydrogens out. Hydrogen atoms are not shown, but carbon has to have 4 bonds. So we know that this carbon actually has 2 hydrogens attached, right? These 2 hydrogens right here. Okay, so we have to be able to interpret those. All right. Well, if we look at this practice problem here, so I don't know if it's a practice problem or just some practice problems that I came up with anyhow. It says practice identifying the location of carbons and hydrogens in a skeletal structure or a bond line structure. In your mind's eye, you should see where the hydrogens, see where they are, and see where the carbons are and see where the hydrogens are located. Look, I'm just going to pick a carbon at random here. I'm going to highlight this carbon right there. Okay, I just highlighted it in yellow. There is a carbon because that is a junction. Can anybody tell me how many hydrogens are attached to that carbon that I just highlighted in yellow?
1.
Exactly. There's only 1. How do you know, Mr. Dion? Because there's 1, 2, 3 bonds shown. We leave out the bonds to hydrogen. So therefore, we know that there is a CH here, right? If I circle these 3 endpoints, could anybody tell me how many hydrogens would be attached to the carbons on the endpoints? Again, not a trick question.
3.
Absolutely, right? Because if we're at an endpoint, there's only 1 bond, so that means that all of these endpoints are CH3s. This is a CH3, this is a CH3. I'll be glad when I don't have to draw these in anymore for you guys. And I probably don't, but I just want to make sure you're with me. And then lastly, if we look at these 2 carbons here, sorry, this carbon and this carbon, they both have 2 bonds, so both of those are CH2s, okay? Both of those are CH2s, like that. I'll try another one. What if I highlight this carbon here? Again, could anybody tell me how many hydrogens are directly attached to this carbon? Yeah, the answer is 1, right? The answer again is 1. So there we go. And you should be able to fill in all of these. You have 3 hydrogens here. You have 3 here. And you have these 2 both have 3. In the interest of time, I'll just not draw them in. Well, now let's, turn up the heat here and see if we could draw in all the hydrogens on this molecule down here. I'll go through it with you kind of slowly. But if you look at the sulfur, since sulfur is a heteroatom, and if you're like, what's a heteroatom, Mr. Dion? Well, a heteroatom is simply an atom that's not a carbon atom. So we draw the hydrogens that are attached to heteroatoms. But if we look at this carbon right here, we know that there's 1, 2 hydrogens attached to it. I'm going to ask you guys another question. How many hydrogens are attached to this carbon that I have highlighted in yellow now?
0.
Absolutely. There's none, right? Because it's got 4 bonds attached to it. So there's no hydrogens there. What about this one here? Are there any hydrogens attached to this one? Is that a yay or a nay?
0.
Absolutely. Yeah, you're absolutely right. So I'm just going to go and fill in the rest. We know that this carbon only has 3 bonds, so there's a hydrogen here. All right, we're going to have 3 hydrogens here. There are no hydrogens here because there's 4 bonds. We have 3 hydrogens here. Oh, good gravy. I have to fill all these in. So there's 2 of them here. There's 1 here. And there's 3 on each of these. And then that's the last time I'm going to do this. Okay. All right. Getting tired of it. All right. There we go. All right. So bond line structures. Now, there are some rules that you have to follow. I don't remember if they're exactly on page 54 of the e-text, but on the hard copy, that's what page they were on. It says if you're given a Lewis structure or a condensed structure, you must be able to draw the corresponding bond line structure. Again, we use the zigzag format when we're dealing with sp2 and sp3 hybridized atoms in a straight chain. So here, since I have 4 carbons right here, let me show you how you would draw this. I mean, there's the answer right there. But you start with your pencil touching the page. When it touches the page, you see that dot that I just made? That's the first carbon. So 1, 2, 3, 4. Now there's somebody that's thinking, could I draw it like this? 1, 2, 3, 4. I don't care. Either way, it represents the exact same thing. Okay, well, let's move on from there. It says when drawing double bonds, try to keep all the bonds as far apart as possible, right? That's just applying your valence shell electron pair repulsion theory, right? So here you'd want to have a bond angle of 120 degrees, right? I love this thing where it's like bad, right? It's a bad molecule. Anyhow, But if you're drawing single bonds, the direction in which the bonds are drawn is really irrelevant, right? Because when you have a sigma bond, right, there's free rotation around this bond and there's free rotation around this bond. So if you want to draw these pointing down like that, well, it's either way, it's going to be representing the exact same thing. All right, well, let's switch gears. And nope, sorry, I have one more slide about bond line structures. Yeah, this is the last one. It says all heteroatoms. So again, I told you this a couple of seconds ago that a heteroatom is just an atom that is not, it's an atom that's not carbon and hydrogen. So a heteroatom would be oxygen, sulfur, nitrogen, the halogens, etc. Okay. If you have a heteroatoms, any hydrogens that are attached directly to a heteroatom, you draw those. Okay, you draw them explicitly. So since we have a hydrogen attached to this oxygen, we draw it out explicitly. You can't leave that out. Another one is another cardinal rule. It says never draw more than 4 bonds to a carbon atom. Okay, a carbon cannot exceed the octet rule. Yes, there are atoms in the periodic table that can exceed an octet. However, those are atoms that come from the 3rd period and beyond. And carbon is in the 2nd period of the organic, or sorry, the 2nd period of the periodic table. Something I was thinking about is one of my students told me that when you have, you know, I told them that when I was in industry and we'd interview somebody, if they ever drew 5 bonds to a carbon, and don't draw this, okay, it's a big no-no, but if they ever did this, you know, we you know, kind of just say there's no way in heck we were going to hire this person. You know, they don't even know basic organic chemistry. But I saw maybe on Twitter or somewhere they call it a Texas carbon. Anyhow, there's no such thing as a carbon with 5 bonds. That's a big no-no. All right, well, let's move, and this is where we switch gears to something called functional groups. If you look back to the chat this morning, right before class started, I posted a link to a video on my YouTube channel where I cover all of the functional groups. And this is something kind of big that you have to have memorized for quiz number 2, and that is all the functional groups that are in table 2.1. Now, again, the page number, I'm not 100% sure, but I know it's table 2.1, and you need to know how to recognize functional groups. Now, let's take a look at those functional groups. So if you're like, I need to know all these, yes, but keep in mind that I said here, you don't have to worry about the compound names. You just have to know the parts that are in red. So you have to be able to recognize the functional groups. And again, I have a video where I go over all of these on my YouTube channel. So YouTube video, anyhow, and you can take a look at that, but let's take a look at it quickly. Whenever you have a triple bond between 2 carbons like this, we call that an alkyne. So this is called an alkyne when you have a triple bond. Now, the first question that you might be asking is, what the heck is R? Okay, what is R? I don't remember element R being in the periodic table. Well, R is actually identified down here. It says it actually refers to the remainder of the compound. So usually carbon and hydrogen atoms. One of the skills you develop in organic chemistry is being able to look at a molecule and identify what's really important for what you're trying to do, and then what is not really of interest, okay? So R is usually just going to be something that's a hydrocarbon. And if you're like, what's a hydrocarbon, Mr. Dion? It's something that's only going to contain carbons and hydrogens. So that's what the R means. It's something that's not really of consequence when we identify the functional group. If you have an R group attached to an OH, like this, okay, an OH we actually call it a hydroxyl, but anyhow, that's an alcohol. So now you know what an alkyne and an alcohol are. If you have an oxygen that is sandwiched between 2 R groups, now here they make it look like the 2 R groups are identical. They could be, but you could put a prime on one of them to represent that maybe they're different, okay? And that would be an ether. Now, an example of an ether would be diethyl ether, which you probably, some of you may have heard of. It used to be used as an anesthetic. Not anymore. It's pretty dangerous, but it's also highly flammable. Anyhow, the next one is, if instead of, you see in an alcohol we have OH, if you have an R group and then SH, we call that a thiol. Thiols are very stinky. The next one is a sulfide. You kind of see that a sulfide is the sulfur, you know, analog, or the sulfur variety of sulfide is the sulfur variety of an ether. So it's where you have a sulfur sandwiched between 2 R groups. The next one is an aromatic. You can see that we're into bond line structures right away. If you have a 6-membered ring With double and single bonds alternating, we call that an aromatic. So now we've covered sulfide and aromatic. Next is a carboxylic acid. You probably saw these in General Chemistry 1 and General Chemistry 2 when you talked about weak acids, like acetic acid, for example, is a weak acid. It's a carboxylic acid, not nearly as strong as something like HCl or sulfuric acid or nitric acid, right? And how do we know that we have a carboxylic acid? It's when you have an OH bound to a carbon with a double bond to oxygen, like this. So a word you're going to hear me say a lot is carbonyl. Whenever you have a carbon with a double bond to an oxygen like this, we call this a carbonyl. Carbonyl. So we have a carbonyl, and then you have an OH bound to it. That's a carboxylic acid. Next, if you have a carbonyl with a halogen attached directly, so X means a halogen, it means chlorine, bromine, or iodine. And if you're wondering, like, Mr. Dion, why didn't you include fluorine? That's a halogen. We're not going to look at a whole lot of acyl fluorides in this class. I'll just kind of leave fluorine out. But anyhow, that's called an acyl halide. Okay, so an acyl halide. If it's chlorine, it's called an acyl chloride. If it's bromine, it's an acyl bromide, acyl iodide. The next one is an anhydride. So if you have two carbonyls and you have an oxygen in between them, we call that an anhydride. Next is an ester. Esters have really fruity smells, like, you know, apples and oranges and cherries and what else? Pineapple, things like that. Those are esters. So if you have a carbonyl and then you have an oxygen and then R group, that's an ester. So now we've covered ester. The next one is an amide. It kind of looks like an ester, but you replace this oxygen with a nitrogen. So we have an amide. Next one is an amine. So if you just have a nitrogen with R groups attached to it, that's called an amine. And then we have a couple more over here on this page. So first is an alkene. If you have a double bond between two carbons, that's called an alkene. Then we have a carbonyl between two R groups, that's called a ketone. And then a carbonyl with a hydrogen attached, we call that an aldehyde. There's one more in here, or one more that's not in here, I should say, and that's a nitro. So if you have an R group with NO2 attached to it, we call that a nitro, okay, a nitro compound. And you might, you know, I've taught this class a lot of times, and, you know, you might say, whoa, baby, you know, it's a lot to memorize. Well, it is a lot to memorize, but just like learning any new subject in life, there's always some vernacular that goes along with it. Yes, this table is in the textbook. This is table 2.1 in your e-textbook. Now, how do students learn functional groups? A variety of ways. I would say flashcards is probably a good way to do it. I would recommend watching my video because I go through it much slower than I just did with you. And also doing the practice problems from the textbook, right? Something else, I just want to take a quick break here with you, is I've had some students emailing me questions about the homework, which is totally fine, you know, no problem. I like answering questions about the homework. But just a bit of advice for you is, let's say we finish chapter 2. I wouldn't jump in the homework right away, okay? I would always start with the suggested practice problems from the textbook. I would do all of those first, then I would start tackling the homework once I've gained some confidence in what I'm doing. Anyhow, all right, functional groups, a lot to know, and I'll tell you what we're going to do. Next class, so what's today? Wednesday? On Friday, the first thing I'll do when we start Friday's lecture is I'll have a couple of compounds that I'll just draw in front of you, or you'll draw them while we're waiting. And the first thing we'll do is try to identify some functional groups as a group, okay? Groups as a group, all right? So that's why we're not looking at it now, because I want you to have some time to look at them. Well, let's talk about formal charges. We discussed how to calculate formal charge in chapter 1. We said the formal charge was equal to the number of valence electrons, subtract the number of sticks, subtract the number of dots, right? Or valence electrons, subtract the number of bonds, sigma bonds, subtract the number of unpaired electrons, right? That's the formula that's used in our book. All right, it says here, a carbon is going to have 4 bonds when it does not have a formal charge, right? Just think about the simplest possible organic molecule, which is methane. I'll draw it here. Have to be kind of draw it small, but the carbon has 4 bonds, 1 to each hydrogen. And we know that since carbon has 4 valence electrons, it's got 4 sticks and 0 dots. That means it's going to have a formal charge of 0. But carbon can have a positive charge, and it can also have a negative charge. When it has a positive charge, we call it a carbocation. And in that case, it's going to have a total of 3 bonds. It's going to be sp2 hybridized, and it's going to have one empty orbital, one empty p orbital. Anyhow, if you look at all 3 of these carbons that are highlighted in green right here that all have a positive charge, the math is identical for all of them. Let's take a look. The carbon has 4 valence electrons. Subtract 1, 2, 3 sticks. So 4 minus 3. But there's no dots surrounding it. So 4 minus 3 gives you plus 1. And the same thing applies here, and the same thing applies here. Again, we call that a carbocation. And carbocations are going to be really important in this class in order for us to understand reactivity. We can also have what's called a carbanion, right? A carbocation had a positive charge, and a carbanion has, you can probably guess, a negative charge, right? A carbanion has 3 bonds, but it has a lone pair. And in that case, it's going to be, or because of that, it's going to be sp3 hybridized. So again, carbocation, sp2, carbanion, sp3. Let's practice calculating our formal charge. Carbon has 4 valence electrons. Subtract 1, 2, 3 sticks, 3 bonds, right? Subtract 2 unpaired electrons. 4 minus 3 minus 2. Don't even need a calculator in organic chemistry. It's all the kind of math you can just do in your head, right? And we get a charge of minus 1. And that is why we put a negative sign by our carbanion, by our carbon with a negative charge. Well, let's talk a little bit more about formal charges. It says here that formal charge, and again, we covered this in section 1.4, so this is old material already. We're already doing a review in organic chemistry. Formal charge, the reason it's so important is because it not only affects stability, but it affects the reactivity of molecules, right? And if you've spoken to any friends, or if you've looked ahead in this class, you notice that organic chemistry focuses a lot on reactions. And so in order for you to understand the reactivity of molecules, you've got to be able to identify formal charges very quickly, okay? Now, it's your first day doing this, or maybe not your first day, but you're kind of learning this still, so it might seem a bit intimidating at first, but I promise you, if you stick with it, after a few weeks or a few days, you'll be able to look at a molecule and identify formal charges very quickly, because let me tell you, the good news is the same old formal charges show up in this class over and over and over and over and over and over and over again. Okay, so you'll get so sick of them, you're like, I know it's a carbanion, move on, right? If we look at the structure on the bottom right, the only structure on the slide, it's incomplete because it doesn't have the formal charges correctly indicated. Formal charges must always be drawn. Fix them by adding them. Now, I'm going to assume that everybody did this problem before coming to class, because I told you the best way to protect your investment, the best way to master the content, is to read the slides before coming to class, try the practice problems, at least give them a go. So can anybody identify, or just, and it's not easy to do this over Teams, but just kind of describe maybe where a formal charge might be in this compound? There's a few of them.
The oxygen to the far left.
The oxygen to the far left, absolutely. Could you tell me what the charge would be on that oxygen? He's talking about this one right here.
Yep, and that would be +1.
Yeah, it's +1, absolutely. So there's a positive charge on that oxygen. How did the student know that? He knew that because he said, well, oxygen's got 6 valence electrons. It's surrounded by 3 sticks and 2 dots. That gives me +1. Bada boom, bada bing, right? Okay, anybody else? Somebody says the nitrogen with a lone pair. The nitrogen with a lone pair doesn't have a formal charge, because this nitrogen has 5 valence electrons. 5 subtract 3 and 2 gives you 0. So that nitrogen doesn't have any formal charge. Anybody else? -1 on the right oxygen. That's what Skylar says. And Skylar is 100% correct. There's a negative charge here, right? You have 6 valence electrons per oxygen. Subtract 6 dots and 1 stick equals -1. Yes. Are there any others? The nitrogen without the lone pair. Yes. Sarah Chancellor says, okay, and she's 100% correct, right? This nitrogen has a positive charge. 5 valence electrons minus 4 sticks and 0 dots equals +1. And there we have it. Oh, that's it. That's all of them. Okay, that's the only formal charges in this molecule. There are 3 of them. So we have Positive charge here, positive charge here, and a negative charge here. So overall, the charge of this ion would be what? Would be +1, because you have +2 and -1. Anyhow, there you go. And if you're like, oh, come on, you guys, I need a little bit more time to think about this. Well, what you would want to do is you would want to start practicing as soon as you can, and be patient, and you'll learn it pretty quickly. Well, the next few slides I'm going to go over a little quickly with you, and the reason why is because the concepts that are on the next 2 slides show up almost Avogadro's number of times in Chemistry 3101. So much so that eventually you'll be able to recognize formal charges on oxygens and nitrogens in your sleep. Okay, so oxygen, and that's what the focus of this slide is. We're talking all about oxygen, right? Oxygen has 3 possible bonding patterns, the same 3 patterns for any second row atom with 5, 6, or 7 valence electrons. Anyhow, if we look on the far left of this table, you see that when oxygen has 3 lone pairs and 1 bond, it's going to have a -1 charge. Okay. You also notice that right here they left the lone pairs out. Now I have a saying which is friends don't let friends leave lone pairs out, and that's something that we might do, and I really try not to do it, okay, because I'm a teacher. But it's something that you will see throughout the book. Sometimes they leave lone pairs out, and they'll be implied. Anyhow, when oxygen has 2 bonds and 2 lone pairs, it's got a no charge, just like in water or ethanol, which is shown here. And when the oxygen has 3 bonds and 2 lone pairs, it's going to have a positive charge. We use the exact same formula that we did on the last slide and we did in chapter 1. If we look at nitrogen, if nitrogen has 2 bonds and 2 lone pairs, it's going to have a negative charge. We see that over here. If you're lost, if you're like, what the hell are you talking about, Mr. Dion? Look, let's do it again. This nitrogen is in group 5A in the periodic table. Therefore, it has 5 valence electrons. Subtract 1, 2 sticks. So let's take that -2. Subtract 1, 2, 3, 4 dots. Let's get a calculator out. 5 minus 2 minus 4 gives you -1, and that's where that negative charge comes from. If the nitrogen has 3 bonds and 1 lone pair, it has no charge in the middle. And just as we saw on 2 slides ago, we saw a nitrogen with a positive charge, didn't we? And it's because the nitrogen had 4 bonds and no lone pairs. Okay, I'll do it one last time. Look, nitrogen, 5 valence electrons, -4 sticks and 0 dots gives you +1. These 3 bonding patterns here in this table, and if I back up to these 3 bonding patterns here, again, you are going to see these so many times in this class that you will get sick of it, okay? You will be able to recognize these bonding patterns very, very quickly. Well, with that in mind, let's turn our attention to a practice problem. This is question 2.8. Okay, at first it asks you to draw all the lone pairs on each oxygen in the following structures. Well, and I'm going to redraw this one just so I have a little bit more room. Okay, so I draw this and I put my negative charge. I'm just redrawing it so I can draw in my lone pairs. Well, if the oxygen has a negative charge and it's got 1 bond, can anybody tell me how many lone pairs must it have?
3.
Absolutely, right? It's got to have 3. 1 lone pair, 2 lone pairs, 3 lone pairs. How did you know that, Mr. Dion? How did the students know that? Because they saw it right here, okay, from the table. If you're thinking, well, that's pretty quick. Yeah, okay, it is quick. All right, let's take a look at the next molecule. Here we go, like this. Now this oxygen is neutral, right? It's got no charge. So could anybody tell me, when does oxygen neutral? When it's got 2 bonds and how many lone pairs? Not a trick question. Absolutely.
4.
2 bonds and 2 lone pairs, okay? So a lone pair, remember, is a pair of electrons. And then lastly, if we look at this one here, I'm not going to redraw this one, there's space here. This oxygen has a positive charge. So oxygen has a positive charge when it's got 3 bonds, like it does here, right? We've got 1, 2, 3. And how many lone pairs?
1.
1 lone pair. Thank you very much. Okay, so I see that my students are pretty quick on this. Hopefully I'm not spending too much time on it for you and boring you. I promise you we're going to get into things that are a lot more interesting, but this chapter is kind of really your real initiation into organic chemistry and making sure that you can draw compounds and recognize functional groups, recognize formal charges. And the reason why you've got to be able to do that is you've really got to be able to do that in order confidently in order to understand reactivity, right? And that's where we're getting to. Okay, we want to get to reactions. Look, if you're like, Mr. Dion, come on, man, just get to the reactions. When do we blow something up? When do you teach us about TNT? You know, when are you going to teach me about cocaine? You know, when are we going to talk about heroin? You know, can we do that now? I want to make crystal meth. You know, teach me how to do that. I'll show you how to do that. Okay, but in order for you to be able to understand, you know, all illegal drugs and how to understand synthesis, this is what you got to start with, right? Okay. Anyhow, let's switch gears and take a look at section 2.6, a really fun section, and it talks about bond line structures in 3D. Now, some of you might be thinking, 3D? Now, what the heck are you talking about 3D for? Because you're drawing everything on a screen, man. How are you talking about 3D? Well, molecules are actually three-dimensional, aren't they? Right? If you think about, you know, a tetrahedron, it's a three-dimensional structure, right? So how do we represent that tetrahedron? And if you're thinking, well, I looked at that in general chemistry, Mr. Dion. You did, absolutely. And we're going to look at it in even more detail here. Why? Because organic chemists have developed a number of ways to represent molecules in 3D that are just helpful depending on the situation, right? Anyhow, so it says here it's difficult to represent a three-dimensional molecule on a two-dimensional piece of paper or a blackboard or a computer screen or an iPad or a tablet, whatever you're using, right? It's not that intuitive. So what we do is we use dashed or solid wedges to show that groups are pointing back into the paper or they're coming out of the paper. Let me show you what I mean here. You see this compound here. Here, let me ask you let's do a pop quiz. This compound that I just circled in red, could anybody tell me how many carbons are in this molecule? That's not a trick.
6.
Exactly. Yeah, there's 6 carbons in that molecule. Anyhow, so this bond to chlorine here, this is what we call a wedge. So maybe I should color code it the same way it is here. So this is called a wedge, okay? Wedge, and this is coming out of the page, okay? It's coming right towards us, right? You see these dashed ones here? This is called a dash, okay? And this is going into the page, okay? Now, something that we're going to look at a little bit even this semester, if you're like, what the heck is this, Mr. Dion? What is that? That's actually called a bicyclic structure. Going back to cocaine, cocaine is a bicyclic structure. Anyhow, so what's going on here in this molecule is that you have a 6-membered ring here. You have 6 carbons in a ring that I'm highlighting in yellow. And then you have a bridge, right, coming off of these 2 carbons here, right? This is a carbon here in between them. Anyhow, let me ask you a tougher question. And it's not meant to be a mind-boggling question. Can anybody tell me how many carbons are in this structure? This is just kind of reviewing what we looked at today. Let's see. I don't see the right answer yet. There we go. A couple people got the right answer. The answer is 7. If you're like, well, where are the 7 carbons? Let me show you. There's one here, 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 and here. So those are 6. But remember, this bridge, this is a junction right here. So there's a carbon in here as well. So there's a total of 7 carbons in that molecule. Anyhow, besides using dashes and wedges, we have a bunch of other ways that we can represent compounds. The first one is called a Fisher projection, shown here. Now, a Fisher projection, we're going to use those mostly in the carbohydrates chapter, which doesn't show up until organic chemistry 2. But we will talk about, and if you're like, oh, good, I dodged that bullet. Well, not entirely, okay? Because we will look at Fisher projections in chapter 5. And I'll just tell you quickly that in a Fisher projection, any bond that's horizontal is actually a wedge. So these are wedges. We don't draw them that way, but anything that's horizontal is a wedge, and anything that's vertical is a dash. Okay, so anything that's vertical at all is a dash. Anyhow, that's neither here or there right for this second, but that's called a Fisher projection. The next one is what I call a Haworth projection. I hear some people pronounce it a Haworth projection, whatever. Anyhow, a Haworth projection is also used for cyclic compounds. Now you can see that these 2 groups, the hydrogen and the hydroxyl, are above the ring, and then these 2 are below the ring. And then this one here is for a bicyclic, and we'll actually get some practice drawing these. this semester. And again, those are used for bicyclic compounds. The way that they represented this compound kind of on the last slide was they said you have a 6-membered ring, right? 1, 2, 4, 5, 6. And then you have the bridge, right, in between, which is this carbon right there. Anyhow, and then obviously you have this OMe that's pointing down, so OMe, and then you have the hydrogen pointing up like that. Anyhow, now if you're wondering, what's the point of all this, Mr. Dean? Why do you have to show us, Avogadro's number of ways to represent these things? Okay. The answer is we have different tools depending on the situation, right? If you think about hammers, how many types of hammers are there? A hammer is just a hammer. No, you got sledgehammers, ball peen hammers, tack hammers, right? Roofing hammers. All right. I'm not sure what you mean by problem. Oh yeah, there is another carbon in here. There is. Yeah, I was testing you. Here you go. There you go. There's 8 carbons in there. Sorry, my mistake. All right, let's keep moving. All right, introduction to resonance. I don't think this is an introduction for anybody because you would have looked. If you have your microphone on, if you could turn it off, that'd be great. Yeah. So if you took general chemistry, you should have been introduced to the concept of resonance. Okay. Now it says here that pi bonds and formal charges are often more spread out than a bond line structure can imply. Now, something I want you to keep in mind while I'm lecturing for the next, next few minutes, is that electrons have energy, right? Electrons are high energy. They're like hyperactive children. If you give them a place to move, they will. Okay, electrons love to move. So if we look at this allyl carbocation, if you're wondering what's that, that's this thing right here. This is an allyl carbocation. Okay, in this case, you have a pi bond, right? This is a sigma bond. This is a sigma bond, but this is a pi bond, isn't it? Okay, it says the pi bond and the positive charge are inadequately described by a bond line structure. It says here that there is a p orbital on carbon 1, 2, and 3. What's the shape of a p orbital? Sometimes my students call it P for peanut, right? The p orbital looks like this. So what I'm saying is this. This is an sp2 hybridized carbon. This is an sp2 hybridized carbon. And I told you earlier on today that a carbocation is sp2 hybridized. Therefore, they all have an unhybridized p orbital on them. I'm going to draw it to the best of my ability. I am not an artiste, okay? But here's the p orbital drawn on each one of those. Okay, so we have a p orbital on all 3 of these carbons. So the pi bond is actually delocalized between carbons 2 and 3. Now, if you're wondering, what exactly does that mean? What it means is that the 2 electrons in the pi bond, right? Any bond consists of 2 electrons. They are not localized between carbons 1 and 2. If you're wondering what does localized mean, it means, stuck in one position. Let me show you what I mean. If all of those carbon atoms have unhybridized p orbitals, now this is a much better drawing, then all 3 of them are going to overlap side. It says side on side. It should be side by side, but whatever. Anyhow, and they're going to look something like this, right? Because I told you this during the last, in chapter 1, I said that when you have adjacent p orbitals, that they actually overlap like this, right? They're actually touching. So all 3 of these are actually touching on the top and on the bottom, above the plane and below the plane. All 3 overlapping p orbitals allow the electrons to move throughout the overlapping area. And so we say the molecule has resonance, meaning it has delocalized electrons. You notice that the pi bond isn't even shown in this representation that's on this slide. Why? Because when the p orbitals overlap like this, it's as if they form a conduit, okay, where the electrons can move between all 3 orbitals. Therefore, that representation that you saw in the last slide, where it just showed the double bond being right here between carbon 1 and 2, it's not completely accurate, is it? Right? Because we're saying that these 2 electrons, the 2 electrons in the pi bond, okay, 2 electrons in pi bond, they have freedom to move between all of those unhybridized p orbitals. And that's what resonance is. So the question is, how can we use a bond line structure to adequately describe the positive charge on the allyl carbocation, right? If those electrons are moving around, then where's the positive charge? Is it on carbon 3 or is it on carbon 1? It says here that the pi electrons can exist on both sides of that central carbon, so we can draw 2 different resonance structures to represent the same compound. Okay, so what we had initially drawn was this, right? We just drew the allyl carbocation like this. But then we said this is not completely adequate, is it? Because we have the 3 overlapping p orbitals and the 2 electrons in the pi bond are free to move around. Well, if they're going to move, so is the positive charge, right? If these 2 electrons decide to move over here, well, then the positive charge is going to move over there, like that. This arrow in between these 2 structures that are called resonance structures, this is called a resonance arrow. So resonance arrow. Okay? This is not a resonance arrow. This is an equilibrium arrow, right? You would have done a whole chapter in general chemistry too where you studied equilibria. But this is a resonance arrow. It's a double-headed arrow. It is not the same thing as an equilibrium arrow because these 2 structures are not in equilibrium. And what do I mean? They're simply not in equilibrium with each other. These 2 structures are used to represent the overall structure. Okay? Now, let's get some more detail on this overall structure, what we call the resonance hybrid. Because neither of those contributors, and what I mean by contributors is just these 2 structures, neither of these really exists. Okay? The average hybrid is much more accurate. And if you're like, what is going on now? Look, we're saying that since the electrons in the pi bond could be on this side or this side, and electrons are hyperactive, that means they're going to move quickly. That means that those 2 electrons are actually, sometimes they're here and sometimes they're there, right? They're kind of shared between all 3 of those carbons. And so instead of drawing a single pi bond, we draw this dashed line here to represent the pi bond. And instead of drawing an actual full formal charge, we draw a delta plus, which just means a partial positive charge. And we call that the resonance hybrid. It's important that you understand that resonance structures are not vibrating or switching back and forth. It's not here and then it goes back here. No, these are just representations of the overall hybrid of the molecule. The analogy that's used in our book is a nectarine, right? If you think about what's a nectarine, well, a nectarine is actually a hybrid of a peach and a plum. But when you're holding a nectarine in your hand, you don't look at it in 1 second, it's a plum, then you blink your eyes and then, oh, all of a sudden it's a peach. No, it has the properties of both a peach and a plum, right? A nectarine has a smooth skin like a plum, but it has the inside, which is more like a peach than a plum. Anyhow, so it's a hybrid. Another example that's sometimes used in textbooks is a burro, right? If you take a horse and a donkey, right, you're crossing a monocot and a dicot for all my biology students out there, and you end up making seedless fruit, right? You make a burro, which can't reproduce, a burro or a mule or whatever it's called. Anyhow, but you don't look at a mule and say, okay, well, now it's a horse, and then the next day you come out and, hey, it's a donkey today. No, it's a hybrid of the 2. Anyhow, delocalized electrons are more spread out. What happens when the electrons spread out? It stabilizes the molecule. Electrons, and I'm right here, electrons exist in orbitals that expand a greater distance, which gives the electrons freedom to move, minimizes repulsions, and electrons spend time close to multiple nuclei all at once, and therefore it maximizes their attractions. Anyhow, so the bottom line, all you really need to know is that resonance structures stabilize the molecule. Okay? The delocalization, that's a word you've heard me use a lot already. It just means that the charge is spread out. That's it. Okay? If you think about, I live in one locale. If I'm localized, well, I live in one place. If you're delocalized, I guess that would mean you live, maybe in a hotel 1 week, and then you move down to Pueblo, I don't know, and you're up in Boulder or something. Anyhow, the resulting partial charges are more stable than the full +1 charge. So the bottom line is this, okay? The take-home message is that resonance stabilizes a molecule. All right, well, let's switch gears again and get into section 2.8, which deals with curved arrows. The curved arrows are just as important as bond line structures were. I told you the bond line structures, it's imperative that you understand bond line structures. Okay, you've got to know bond line structures, but curved arrows are just as important. They're going to be used constantly in organic chemistry. It even says here we're going to explore how curved arrows show reactions in chapter 3, but right now we're going to look at curved arrows to help us understand resonance even more. So I'm starting at the top of the slide. It says, in organic chemistry class, we're going to use curved arrows to show electron movement. Now, when I have an arrow, the starting point of the arrow, I call it the tail. The part with the point on it, I call that the head. Notice that the head has a double barb, right? We call this part a barb and this part a barb. It's a double barbed arrow. That means it shows the movement of 2 electrons. There is such thing as a curved arrow that has only 1 barb. Again, this would be the tail. This would be the head. But when you have only 1 barb like this, that shows the movement of 1 electron. That is something that we won't look at until chapter 10, which isn't until late April or May or something like that. So don't even stress about that. That would be a radical when you move 1 electron. We're not concerned with that at all. So all of these arrows that you're going to see, they all represent the movement of 2 electrons, or what? Pairs of electrons, okay? The arrow starts where the electrons are located, and it ends up where the electrons are going, where they're going to end up after the electrons move. So if we look at this curved arrow right here, you see that the tail of the arrow is starting on the pair of electrons in the pi bond. The head of the arrow is ending up between this carbon and this carbon. So that tells me that my double bond is going to move over here. Now I'm just drawing the resonance arrow. If I have 1, 2, 3, 4 carbons, I see that my double bond is going to be here, like this now. And my positive charge is going to end up on this side. All right. Something else that I neglected to point out with resonance structures, I'll just tell you now, okay? I can't be held responsible for all my wheelings and dealings. Is that, just quickly, whenever we draw resonance structures, we always put them inside square brackets, okay? So I told you what a resonance arrow is, the double-headed arrow. Well, square brackets are always used for resonance structures. And it's so important that when my students wrote paper quizzes pre-pandemic, if they forgot to put in the square brackets, I would actually remove a point for that because it's not a proper resonance structure. Also, if they didn't draw their resonance arrow correctly, they would lose points for that. So things, the details do matter in organic chemistry. Okay, the specific rules for using curved arrows. There are specific rules for using curved arrows to describe electron delocalization. Now, this is kind of my introduction for you guys to the book's author. So the author of our textbook is Dr. David Klein. He's a really great teacher. In my opinion, he's a great author. I think he's written a great book and an amazing solutions manual. Now, when I learned organic chemistry way back in the 90s, the book that I used didn't have a lot of rules in it. But David Klein has tried to break things down into rules to try to make it more digestible for students, okay? Now, I see a question in the chat here. Somebody says, how many resonance structures do molecules typically have? And the answer is, it depends. It totally depends on the molecule. You can have 2, you could have 3, you could have 10, okay? It all depends on the molecule. Technically, you could have, limitless, but we won't look at any examples like that. So let's go through the rules. One thing I've learned teaching science students is that science students actually like rules. Like, you know what, Mr. Dion, just tell me the rules, I'll follow them, and then it'll help me get a good grade, right? And I think there's some truth to that, just being able to recognize, patterns and rules. It's a big part of chemistry. So let's go through the rules. Rule number 1, never show a single bond, which is, again, a sigma bond, right? The sigma bond. Never show a sigma bond as being delocalized. So in other words, that's a very fancy way of saying don't break a single bond. Okay, we're never going to see that. Will we see single bonds being broken in this class? Absolutely. In chemical reactions. Okay, in a chemical reaction, not in resonance. Okay, We're never going to see that happen in resonance. And what are we talking about right now? We're talking about resonance. We're not talking about reactance. We're not there yet. Resonance occurs for electrons in existing overlapping p orbitals. Pi bonds and lone pairs are going to be delocalized, not sigma bonds. Okay. And if you look at, anything that I've drawn, right, here was an arrow, but it was on a pi bond. It wasn't on a sigma bond. We're not going to break any sigma bonds in resonance structures. That would be a huge no-no. Okay. Next one is, everybody who's hearing the sound of my voice past General Chemistry 1, you know this rule. Don't break the octet rule, right? Never exceed an octet for a second row element. What are the second row elements? Boron, carbon, nitrogen, oxygen, fluorine. Okay, the first two, don't worry about those. But so it says P block, second row elements, never exceed an octet. Okay, that would be insane. Okay, a carbon cannot exceed an octet. So you see this. I'll just show you an example, like this one right here. If you were to draw what they're trying to represent here, and this is wrong, okay? Everything you see here says bad on it, so don't even write this down. Just watch Mr. Dion make a big error here, okay? You would end up with this, I was going to say a bad word, this junk, okay? You'd end up with this. You'd have that, and you'd have a negative charge on the carbon, technically, okay? But this is impossible. A big no-no. Where's red, okay? Draw a red X through that. Carbon cannot have 5 bonds. That's the old, hey, thanks for coming out, take a keychain on your way home or something like that. No, you are not getting a job, okay? There's no such thing as 5 bonds to a carbon, so that is a bad arrow, okay? I have a 3-month-old at home, and my son, who's 3 years old, he always says to the 3-month-old, he's like, bad baby, bad baby. Anyhow, the baby's crying. Anyhow, next one, we have a bad arrow here. I mean, I'm not going to go over all these. They're so insane. But the same thing applies here. I shouldn't draw these. They just feel creepy. It just feels wrong. But anyhow, you'd end up with something like this, okay? You'd have 1, 2, 3, 4 bonds to a nitrogen and a lone pair. That means it's exceeded the octet rule. Look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No! I'm not even going to do the rest. They're so disgusting, okay? This is just wrong, okay? But sometimes, I'm not a big fan of teaching by showing what's wrong, but sometimes you have to show students example of, what's the word that's even used on here? Look at this word. Violation, right? They're violating, violating a rule, okay? So you don't want to violate rules, okay? No rule violation in organic chemistry. All right. But second row elements, they can have less than an octet, right? They definitely have less than an octet. Anyhow, second row elements, boron, carbon, nitrogen, oxygen, fluorine. Yeah, sometimes they can have less than an octet. We saw that today. I taught you the carbocation earlier on, right? I showed you this. I said, look, you guys. I said, hey, when carbon has 3 bonds and a positive charge, and it's sp2 hybridized, we call that a carbocation. Well, come on. That carbon is only surrounded by 1, 2, 3, 4, 5, 6 electrons. It doesn't have an octet. It doesn't have an octet. Okay, so a second row element, boron, carbon, nitrogen, oxygen, fluorine, they can have less than an octet. Okay, but they're not going to exceed the octet rule. Now, this is a question I have, like I always look at my notes when I'm teaching. Try not to, but anyhow, I noticed that in my notes, I wrote something down here. A student asked me a question. I don't remember when it was. The student asked me a question one time and said, hey, well, hold on. If the oxygen has a negative charge, isn't that a violation of the octet rule? Heck no. This oxygen, right, is still surrounded by, look, 1, 2, 3, 4, 5, 6, 7, 8. So even though it's got a negative charge, it's still not violating the octet rule, okay? You're not going to see that happen again in this class, all right? Well, it says here, in each of the following cases, determine whether the arrow does a violation. Man, we keep talking about these violations. I don't like this. Violates either of the 2 rules and describe the violation, if any. Don't forget to count all hydrogen atoms and lone pairs. Okay, I'm just going to start. I'm queasy just looking at some of these. Anyhow, can anybody tell me, is there a violation in A? Just yes or no? If you want to describe it, be my guest.
Octet rule.
Yeah, big time, right? So the student just said octet rule, but what he means is this is a big no-no. There's a huge violation here. This is a violation of the octet rule. Do not draw, right? Don't attempt this at home. But what is going on here, and this is insane, okay? The student drew something like this, okay, where the carbocation would move over here. Then this nitrogen would have 5 bonds. Impossible. Okay, as we say in French, impossible. Okay, c'est pas possible. Okay, so that's a violation of the octet rule. What about the second one? Is there a violation in the second one? The second one, is there a violation in it?
No.
No, there's no violation in this one, not at all. All right, there's nothing wrong with this arrow, okay? Because if you draw the resonance structure, so we'll draw everything that's not going to change. This pair of electrons from the pi bond is going to go up on the oxygen. So instead of having 2 lone pairs, now you have 3 lone pairs. The oxygen has a negative charge, and the carbon is going to have a positive charge, right? And if you're wondering, how did you know that? We did this already today. Oxygen, when it has 3 lone pairs in one bond, it's got a negative charge. And when carbon has 3 bonds and no lone pairs, it's got a positive charge. So no violation there. And what about the C? Is there a violation here? These are actually kind of funny problems. Is there a violation in C? Yeah, there's definitely a violation in C, isn't there? Right? If you just look at it at first glance and you don't really think very hard about it, you might say, okay, well, hold on, Mr. Dion, let me just draw it out here for you, and let me show you why there's no violation. Look at this. This carbon's only got 4 bonds, but hold the phone. Let me use a different color. What about this hydrogen? That's implied, right? This is a bond line structure. So that means that there is a bond here. So that means there would be 5 bonds to that carbon, and that would be a huge violation. So let me get a red highlighter to make it even uglier, okay? And the answer for both of them that have a problem are both of these exceed octet rule. Okay, the first one for nitrogen and the second one for carbon. C for carbon. All right, C is for carbon. Okay, let me just stop here. Stop recording for a minute. Dun, 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 dun. Stop recording.